So what I notice in this case is we've got a product in the numerator, right? So x to the 3/4 times the square root of x squared plus 1. There's a product rule for sure. Then with the square root of x squared plus 1, the x squared plus 1 is on the inside. There's a chain rule, right? Because I would need the derivative of the inside piece. Overall here, we have a quotient, right? Because we have a numerator and a denominator. And then within the denominator of our quotient rule, we also have another chain rule because we have the 3x plus 2 to the 5th power. We would need the derivative of the inside piece of that. All right, so we have an overall quotient rule, and within that, we have a product with a chain, and in the denominator, we have a chain rule. There's a lot going on there, right? Just finding the derivative of this thing would be a nightmare. I mean, not a nightmare, but it would take a long, long time, right? However, we now know something about logarithms that could help us to simplify this first so that we don't have to use all those rules anymore. Okay, so that's what we're going to do on this problem. So we're going to use logarithms to our advantage so we can actually simplify this fraction first and then find our derivative. Okay, so what I'm going to do is I'm going to take the natural log of both sides of this equation. That's my first step. So we're going to end up with natural log of y equals, and then natural log of everything we've got over here. So x to the 3/4 times the square root of x squared plus 1 over 3x plus 2 to the 5th. So if you're ever asked to differentiate something and you notice, hey, wait a minute, I've got a lot of rules going on in this one. It's going to be a lot of work to try to find the derivative. Simplifying it using natural logs is probably going to be your best bet. Okay. Now, we've got to think back to our properties of logarithms that you probably learned back in pre-cal of how we could actually rewrite this logarithm now. So I'm going to keep my natural log of y on the left. So now let's think about what we can do with the pieces inside this log. Well, what's one thing we're allowed to split up in terms of logarithms? Okay, tell me this. Products, right? Okay, so we can split up products that are inside of a log. When we split them up, though, they become what? What operation do they change to? Addition. Good. So whenever I split up multiplication inside of a logarithm, I'm going to have two separate logs using addition. What other operation can I split up in there? Good. Division is going to become subtraction once I split it into multiple logs. So that's the first thing I'm going to do is I'm going to split up my multiplication using addition. I'm going to split up my division using subtraction. So this is going to become the natural log of x to the 3/4 plus the natural log of the square root of x squared plus 1 minus the natural log of 3x plus 2 to the 5th power. Okay, so anytime you have multiplication inside of a natural log or any kind of log, you're allowed to split that up using addition. Anytime you have division inside of a log, you can split that up using subtraction. Any questions on that step? All right. What's our third property of logarithms now once we split up the multiplication and division? What else are we allowed to do? Good. Any exponents can be brought out to the front now. So I'm going to have the natural log of y equals 3/4 times the natural log of x plus, remember, this is the same thing as x squared plus 1 to the 1/2 power, so I can actually bring out a 1/2 times the natural log of x squared plus 1 minus, and then the 5 can come to the front here, times the natural log of 3x plus 2. Any questions up to that point about using our properties of logarithms to separate all these into multiple logs now? Okay. Now, at that point, we can take our derivative. So on the left-hand side, if you're taking the derivative of natural log of y, what is that going to look like? So think about the derivatives that we looked at yesterday, right? If it was the derivative of natural log of x, okay, good, right? It's going to give us a 1 over y. And then because it's implicit differentiation now, right, we're actually taking the derivative with respect to x. We just have to remember that we're multiplying by a y prime or a dy dx, however you want to write that. Okay, with the derivative of the natural log of y just gives us 1 over y. And then because it's implicit, we need the y prime. Now let's go to the other side. We have 3/4 times the natural log of x. What's the derivative for that term going to give us? All right, so we're going to have 3/4. That's our coefficient. We keep that. Derivative here for natural log of x is just 1 over x. But we're taking the derivative with respect to x, right? So we don't need a dx or anything in this case, right? It's just going to be 3/4 times 1 over x. That's it. So it's only the y terms that we have to remember, that dy dx or the y prime. The x terms, since we're taking the derivative with respect to x anyway, we don't need anything additional there. Any questions on that term? All right, let's move to the next one now. Plus, now we've got 1/2 natural log of x squared plus 1. So how are we going to do that derivative? Or what would it look like? Okay, good. So it is going to be technically a u substitution, right? So if you want to actually write out the steps for that, we'd start with 1/2 natural log. I'm actually just going to do the natural log of x squared plus 1 piece. So natural log of u, where u equals x squared plus 1. So this is going to give us 1 over u times u prime. U prime is just 2x. And so we get 1 over x squared plus 1 times 2x. And again, if you can do that work in your head without actually writing out the u substitution piece, that's perfectly fine. So I'm going to keep the 1/2. I'm going to multiply that by 1 over x squared plus 1. And then that gets multiplied by the derivative of the inside, which is 2x. Any questions on that term? All right, and then the last one here, same thing. It's technically a U substitution. Let's see if we can do it without actually writing out the U part, though. So we have our 5 out front. What's the derivative for natural log of 3x plus 2 going to give us? All right, so we're going to get 1 over 3x plus 2 for this piece, and then the derivative of the inside here is just 3, so it does become 3 over 3x plus 2. Good. Any questions on that line there, finding the derivative of each of those terms? All right, now all that's left at that point is just a little bit of simplifying and some substitution. So I'm going to go ahead in this case and say, well, this is 1 over y times y prime. This right here is just going to give us 3 over 4x if we multiply that, plus, in this case, the 1/2 and the 2 would just give us a 1, so we really only have the x here. So we have x over x squared plus 1 minus, and then here 5 times 3 is 15, so we get a 15 over 3x plus 2. Right, now I'm trying to solve for y prime. So what would I need to do at this point so that we have just y prime? All right, so we are going to do that, right? But I also need to move the y to the other side to get y prime by itself. How am I going to get that y on the other side? Multiply. Good. So I'm just going to multiply both sides by y here. So now we have y prime equals y times everything that we've got over here. So 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. All right, and then like Dean said, now we can substitute the y value, which is the original function, back in for y so that everything's in terms of x again. And so this just becomes x to the 3/4 square root of x squared plus 1 over 3x plus 2 to the 5th times everything we've got in here now. 3 over 4x plus x over x squared plus 1 minus 15 over 3x plus 2. So this right here would be our final answer for our derivative. So again, even that is not a short process, right? There's still some work that has to be done there. Okay, but by using those properties of logarithms, we at least simplify the derivatives for ourselves so that we're not having to do all those weird products with chain rules within them, or quotient with 2 chain rules and a product within it and things like that, right? Any questions about the steps for that one now? Again, just don't forget with implicit, right? You have to have the y prime, and then you're also trying to get y prime by itself in the end, which is why we have to do that substitution of y. So on a problem like this, Dean, no, I don't expect you to combine everything. You could, right? You could find the common denominator over there. You could actually put all those fractions together and then just multiply. That's actually what the final answer would look like if you were to use your quotient rule with your chain rules and your product rules all combined, is you'd end up with one big fraction. But I'm not going to expect you to do that on a problem like this. The only time you would really need that is if you were asked to then find like the min or max and you needed to set it equal to 0, right? Then yeah, you would need to combine everything so that you could actually set your numerator and denominator equal to 0 to find those critical numbers. But in terms of just finding the derivative, this is perfectly fine, okay? Any other questions there? All right, let's try this one now. So again, we want to differentiate y equals x to the square root of x power. Okay, good. Since this case, right, we've got an x to some power, but there's an x in the exponent also, right? Well, it's not just a basic exponential function because our base is x, but it's also not a power rule because our exponent is something other than a number. So we're going to have to do something else, and natural logs is actually going to help us to simplify this one so we can actually find our derivative. So we're going to take the natural log of y. We're going to take the natural log of x to the square root of x. Now, once we do that, what can we do with that natural log on the right-hand side? Good. Now we can take out the exponent, right, and bring it to the front of the natural log. So we're going to have natural log of y equals, I'm going to write that as x to the 1/2 now, times the natural log of x. Okay, so now on the right-hand side, if I'm looking for the derivative, what rule do we have over there now? It's just a product, right? We have x to the 1/2 times the natural log of x. We can solve that using product rule. So now we have a derivative that we can actually find. All right, so let's look at the left-hand side first. What's the derivative for natural log of y going to look like? Good. So we have 1 over y times y prime equals, and now if we do our product rule, we'll let f be x to the 1/2. Our g function is natural log of x. Right, so what's our derivative for f? Good. 1/2 x to the negative 1/2. And what's our derivative for g? Good, that's just 1 over x. All right, so now we plug into our product rule. Again, that's f g prime plus g f prime. So start with f, we have x to the 1/2 times 1 over x plus natural log of x times 1/2 x to the negative 1/2. Right, so again, I'm going to go ahead and simplify what we've got over here on the right first before I move that y over. So what's x to the 1/2 times 1 over x? So we basically have x to the 1/2 over x, right? You could write it that way, right? Square root of x over x. Or I was going to try to combine the x's here. So if you have an x to the 1/2 on top and an x on the bottom, if we subtracted those, what would that give us? Good, right? So just x to the negative 1/2, right? And we can deal with the negative exponents at the end, but in this case, because they're both x's, we can actually combine them. Plus, now over here, I'm just going to go ahead and say, well, I've got my x to the negative 1/2. I'm going to move it to the denominator. My natural log of x is going to go to the numerator. So I have natural log of x over 2x to the 1/2. And again, if you want to go ahead and move this x to the 1/2 now to our denominator, you have 1 over y prime, 1 over x to the 1/2, or square root of x if you want to write it that way, plus natural log of x over 2x to the 1/2. And then, Dean, like you said before, if you wanted to find a common denominator there and actually combine these, this one wouldn't be too bad, right? Because they already both have the x to the 1/2. So you just have to multiply the first one by 2. But again, not necessary. If you wanted to, you could, though. All right, so now what's our next step going to be, though, to try to get y prime by itself? Good. Now we need to move the y over. So we have y prime equals y times 1 over x to the 1/2 plus natural log of x over 2x to the 1/2. And then our final step would be what? Good. Now we can substitute the original function for our y there. So that's going to give us x square root of x times 1 over x to the 1/2 plus natural log of x over 2x to the 1/2. And that's it. So again, just make sure you get everything back in terms of x here, right? Don't leave any y's in your derivative. And that should be our final answer. Any questions on that one? All right. So that's all for section 6.4. So let's take a look now at 6.6, which is our final section. All right, so now we're going to be looking at both derivatives and antiderivatives or integrals for inverse trig functions. All right, so the first thing we're going to do is just kind of to review what is an inverse trig function, right? How can we actually solve and evaluate these things? And then we'll move into what the actual derivatives and antiderivatives look like for these. All right, so first off, if we want to evaluate the inverse sine of 1/2, what is that asking us to do first off, right? If we're looking for the inverse sine of 1/2. Okay, so if you plug it into the calculator, first off, make sure you're in radian mode. I will tell you that because everything we do will be in radians. But if you do that, it's going to give you a decimal, right? I will tell you that. However, we can get an exact value for this based off of our unit circle. So if we're looking for the arc sine or the inverse sine of 1/2, what are we trying to find? Okay, so anytime you're looking at an inverse trig function, you're looking for the angle whose value is whatever's inside here. Okay, so I'm trying to find what angle has a sine value of 1/2. That's my goal. Well, does anybody know what angle in terms of radians would have a sine value of 1/2? Think about your unit circle. We know it's positive, right? So in this case, I'm going to focus on the first quadrant, right? It could be first or second. I'm just going to think about the first quadrant here. And remember, sine is the y value. So we want to know where would the y value be equal to 1/2? Which point would that happen at? Okay, so that would be the ordered pair where the y value would be 1/2. What's the radian measure at the point square root of 3/2 1/2? Pi/6. Good. Okay. So I know it's probably been a little while since you've done the trig, right? Okay, but we can't forget all this stuff because these values will keep coming back up. So just make sure, review your unit circle, make sure you know these values. Okay, so this is going to give us pi/6. In this case, even though there's another value in the second quadrant that would give us positive 1/2, when we're dealing with inverse trig functions, the range here for our inverse sine is only going to be between negative pi/2 and positive pi/2. So that's the only value that we need to get here is just pi/6. Okay. Any questions on getting that value now? All right. Now, the next one, a little more difficult because 1/3 is not a value from our unit circle. So we're not going to be able to do this just in terms of finding those values. We want to find the tangent of the arc sine of 1/3. But remember, I just told you on the last one, the inverse sine or the arc sine of a value just means what is the angle at that value. So all of this right here, the arc sine of 1/3 represents an angle. I'm going to call it theta. Now what I'm going to do is I'm going to draw a right triangle to represent that theta value that we've got there. So I'm going to draw my right triangle. Doesn't really matter what the dimensions are. I mean, it does have dimensions, but it doesn't have to be to scale. And in that triangle now, I'm just going to put my theta. And you could put it up at the top. It doesn't matter, so long as you put theta in there somewhere. Now, if we're looking for the arc sine of 1/3, think about what you know about sine in terms of your right triangles. What does sine tell us about that right triangle? So again, this is telling us that that's right. Sine gives us the opposite side over the hypotenuse. Well, 1/3 is that sine value that we're looking for the angle for. So that tells us that 1 is going to be our opposite side from our angle, and 3 is going to be our hypotenuse. So that's going to go over here. Okay, so again, anytime you've got an inverse trig function, all that represents is an angle. So you can draw a right triangle from that angle. Arc sine is going to give us 1/3, which is opposite over hypotenuse. So we can put that in the triangle. Now, if I'm looking for the tangent of that theta value now, what do I need to know about this right triangle to calculate tangent? Because again, all I'm trying to do now is find what's the tangent of theta, where theta is arc sine of 1/3. But what would I need to know about my triangle to find tangent? We need opposite over adjacent, right? So I'm missing the adjacent side now. How could I find it? So we've got a right triangle. It's Pythagorean theorem, right? So we know our hypotenuse, we know one of the legs, we're looking for the other side, right? So we can use Pythagorean theorem here. So this is just going to be 1 squared plus b squared equals 3 squared. Now 1 squared is 1, 3 squared is 9, so this is b squared equals 8. And if we take the square root of both sides here, square root of 8 is just 2 square root of 2. Okay, so that tells us this side right here is 2 square root of 2. Any questions on that? All right, so then what would our tangent be equal to then? That's it. 1 over 2 square root of 2. Okay, so if you're ever looking for a trig function of an inverse trig function, and it's not an inverse trig function that you're familiar with, right? Like the previous one was 1/2, we could find that from the unit circle. In this case, though, it's 1/3. That's not on our unit circle. Draw your triangle. Think about, use Pythagorean theorem to find any missing sides that you would need, and then just evaluate the trig function from that triangle. Any questions on that one now? Again, just keep in mind, anytime you're looking at an inverse trig function, it represents an angle, right? The inverse sine of 1/2 is what angle has a sine of 1/2. The arc sine of 1/3 is what angle has a sine value of 1/3. All right, now the derivative of our arc sine. Okay, so if you find the derivative of inverse sine or arc sine, it's going to be 1 over the square root of 1 minus x squared. Notice here that x has to be between -1 and 1, non-inclusive, right? So -1 and 1 wouldn't work there because that would give us 0 in the denominator. Anything smaller than -1 or bigger than +1 would give us a negative under the square root. Okay, so that's why our x value has to be strictly between -1 and 1. Again, this is the basic derivative of inverse sine of x. If there's something other than an x in there, then you're going to have to use a chain rule, right, to make sure you have the derivative of the inside. All right, so if f of x is the inverse sine of x squared minus 1, first off, we want to find the domain of f, then we want to find the derivative of f, and then we're going to talk about the domain for that derivative. Okay, so those are the three things we're looking for. All right, now, I told you before, I just kind of mentioned it in passing, the domain for inverse sine in general, okay, so if this was just inverse sine of x, its domain is negative pi over 2 oh, sorry, that's the range. It's from negative 1 to 1. Okay, so we can have values anywhere between negative 1 and 1 inside of our inverse sine, and the range values that come out are going to be somewhere between negative pi over 2 and pi over 2. And notice here, those values are inclusive, right? So we can actually have negative 1 and 1 inside of our inverse sine, just can't have them in the derivative of inverse sine. Now for this one, we're not just looking at inverse sine of x, we're looking at inverse sine of x squared minus 1. So what do you think we're going to do in this case to find the domain for that specific function? Okay, so to find the derivative, we are going to have to do a u sub, right? Okay, but in this case, if we're just looking for the domain, I know the domain of the original inverse sine function is between negative 1 and 1. But now I've got this thing instead of x. So how am I going to find the domain for this one? Okay, so not plug in the negative 1 and 1. Notice here, if this is an x, then x is between negative 1 and 1. But this time, what's inside the inverse trig function is x squared minus 1. So instead of x there, we're going to put x squared minus 1. So we're going to set up the inequality here. Negative 1 is less than or equal to x squared minus 1 is less than or equal to 1. Okay, so this is finding the domain now for that original function. And that'll always be the case, right? We know that the domain for inverse sine is between negative 1 and 1. So whatever's inside there now, we're just going to plug it between negative 1 and 1. Okay. Now, how would you solve this inequality down here? Okay, good. We can add 1, and we just have to remember to add 1 everywhere when we do that. So that's going to give us 0 less than or equal to x squared less than or equal to 2. And then we can do what? Yeah, and if we take the square root here, okay, this is where we have to be careful. When we take the square root, you can't just say, well, the square root of 0 is less than or equal to x is less than or equal to 2 or plus or minus 2 technically, right? So what you would actually probably want to do in this case is say, let's find some critical numbers for this one, which is going to give us plus or minus square root of 2. Right, the 0 is going to take care of itself because the square root of 0 is just 0. It's included. It's between these two values. So now I'm going to put these on a number line, and I'm going to determine which interval or intervals I actually care about. Okay, so I'm going to actually plug something in. What's something to the left of negative square root of 2 here? Okay, so -2 is good. If I plug that in right here, we would have 0 less than or equal to -2 squared less than or equal to 2. Well, what's -2 squared going to give us? It's 4, right? Is that a true statement? Is 4 between 0 and 2? No. So this interval down here doesn't work, right? So anything less than -square root of 2 is going to give us a false statement. That inequality is not true anymore, so we're not going to include those values. All right. Now, what's something that's between negative square root of 2 and positive square root of 2? Let's avoid 0 just because 0 is kind of part of the inequality. Okay, 1 works, right? So that's still between negative square root of 2 and positive square root of 2. So we'll say 0 less than or equal to 1 squared less than or equal to 2. 1 squared is 1. So is this a true statement now? Yes, right? 1 is between 0 and 2. That interval checks out. And you might already be able to see it, but if we test 2 now we're just going to square the 2, which is going to give us 4 again. Is that a true statement? No, and so this right here is not included, and so now we can say the only interval that works for this one is everything between negative square root of 2 and positive square root of 2. So our domain here is from negative square root of 2 to positive square root of 2. And the reason it's inclusive is because both of those inequalities had an equal to, right? So we can include the endpoints for those intervals. And so just be careful, right? Whenever you're solving an inequality like that, when you take square roots, we're going to get pluses and minuses. So it's just really important to kind of test and make sure you know which intervals actually work in that case once you get the pluses and minuses. Any questions on the domain for that function? All right, now let's find the derivative. Okay, so that's part B. So what can we do here to find our derivative for inverse sine of x squared minus 1? All right, good. So we're going to do a u substitution. So I'm just going to go ahead and rewrite this as inverse sine of u, where u is equal to the inside, which is x squared minus 1. All right, now, when we find f prime of x, this is where that formula comes in from the previous slides. This is going to give us 1 over the square root of 1 minus u squared, and because it's a chain rule, we have to multiply by u prime. Right, so we get 1 over square root 1 minus u squared, and then times u prime. All right, so now we just need to know our u prime value. So what's the derivative for u going to give us this time? Good, u prime is 2x. So now we have f prime of x equals, now we can substitute our x values back in here. So this is going to be the square root of 1 minus x squared minus 1 all squared times 2x. So then if you want to, right, we can go ahead and multiply out the x squared minus 1 squared, combine like terms inside the square root here. We can also move the 2x up into the numerator. So we've got our 2x over square root 1 minus x squared minus 1 squared is going to give us x to the fourth minus 2x squared plus 1. And in this case, the 1 minus the 1 that's inside the parentheses here, those are going to cancel out. And so we're left with 2x over the square root negative x to the fourth plus 2x squared. Okay. And I'm fine if you leave it like that. If you really wanted to, you could take out an x squared from that square root, which would give you an x on the outside. It would actually cancel out the x in the numerator. So there's some more simplification you could do. Okay, but if you got to that point, I'm good. Any questions about that derivative? All right. Now, the last piece of this one is we want to know the domain for f prime. So how are we going to find the domain for f prime now? And I'll go back and show you. We know in this case, right, for the derivative that the x value has to be somewhere between -1 and 1, non-inclusive though, right? So that's the only difference between what we did in part A and what we're doing now. In part A, we could include the endpoints, the -1 and the 1. Here, we're not going to be able to. So our initial setup is going to be -1 is less than x squared minus 1 less than 1. Now, to solve this, it's going to be very similar, right? We can add the 1. That's going to give us 0 less than x squared less than 2. And then our work is going to be very similar to what we did previously. The main difference now, notice this 0 is no longer included. So when we actually do this, we're still including all the values between negative square root of 2 and positive square root of 2, except we can't have 0 in there anymore, right? Because there's no equals on the 0. So what do you think this interval is going to look like then for our domain for the derivative? All right, so I agree that it's going to be open on each end, right? So we're going to go negative square root of 2. Same thing with the positive square root of 2. But again, we can't include 0 either, and 0 is between those two values. So what else are we going to have to do here? Good. So it's going to actually go from there to 0, and then we're going to have a separate interval now from 0 to square root of 2. This is actually the domain for the derivative, okay? So we didn't have to worry about the 0 on the previous one because 0 was included And so we could just go straight from negative square root of 2 to positive square root of 2. But on this one now, because the 0 is not included, now we have to break our interval at 0 and not include that value. And if you think about it, right, if you look inside the denominator of this one, if you put 0 in there, you're going to get square root of 0, which is 0 in the denominator. It's undefined there. That's why we can't include 0 as part of the domain for our derivative. Okay. So again, the 3 parts to this one. There's the domain for the original function. This is our derivative. And then we have our domain for our derivative down there at the bottom right. Okay. Now, on a test, right, I'm only going to be asking for the derivative. I'm not going to worry about the domain pieces of these, but there could be some in the homework that do ask for domains. So just make sure you're comfortable finding that for the homework. Any questions on that one now? All right, let's go ahead and take our break right here. Okay, so I've got 10:57, so we'll say 11:02. We'll get started back with example 3. All right. So derivative of arc cosine. So we looked at the derivative of arc sine. Now the derivative of arc cosine, very similar. The only difference now is we put a negative in front, right? So if you know the derivative for arc sine, all you got to do is put a negative in front of that. That's your derivative for arc cosine. Domain, again, exactly the same as arc sine, from -1 to 1, non-inclusive, because again, that would give us 0 in the denominator if those values were included. All right, now what we want to do for example 3 is we want to express the cosine of the arc tangent of x, okay, in a simplified form now. So this is similar to that second example, or sorry, the first example that we did on the second part, where we actually had to draw the right triangle and think about what those relationships were between the sides. So remember, whenever you see an inverse trig function, that's going to represent an angle, right? So arc tangent of x is just a theta value. So what we're really trying to find here is cosine of theta. So we're going to do the same thing we did. We're going to draw a right triangle here. We're going to put our theta value in our right triangle. But now we have to think about what we know about that right triangle this time. So if we're looking at arc tangent of x as our theta value, what information do we have about our triangle? Okay, good. So tangent gives us the opposite over the adjacent. We could think of x as x over 1. So now we know the opposite is x. We know the adjacent is 1. Perfect. Okay, so now if we're looking for cosine of theta, what sides do we need? We need adjacent and hypotenuse. Good. So what are we going to have to do to find our hypotenuse this time? Good. So we got x squared plus 1 squared equals c squared. In this case, x squared plus 1 squared is just x squared plus 1. And then we can take the square root. So square root of x squared plus 1 is c. Don't try to simplify this, right? There's addition inside the square root. You can't split it up. So the hypotenuse here is just the square root of x squared plus 1. All right, now that we know the hypotenuse, what's the cosine of theta going to be equal to then? Good. 1 over the square root of x squared plus 1, right? Because that's our adjacent over our hypotenuse. That's how we calculate cosine. So again, very similar to what we did on example 1, part 2, except now instead of a value, right, that one we had 1/3, so we had a 1 and a 3 to plug in. Here we only have the x, so we have to use x as our opposite side, 1 as our adjacent side, and then just get everything in terms of x here. Any questions on that one? All right. Now limits. Okay, so our limit as x approaches negative infinity for the arc tangent of x is going to be negative pi over 2. And the limit as x approaches positive infinity for arc tangent x is going to be positive pi over 2. Now, what does that tell us then about the graph for arctangent of x? So these limits as x approaches negative infinity and positive infinity. What does that tell us about our graph? Horizontal asymptotes. Good. So remember, whenever you get a specific value as your limit as x approaches negative infinity or positive infinity, now we know there's going to be horizontal asymptotes for that graph. So what this graph looks like, okay, if you don't remember arctangent, we're going to have a horizontal asymptote at negative pi over 2. You're going to have a horizontal asymptote at positive pi over 2. It's approaching the negative pi over 2 as we go to negative infinity. It's approaching positive pi over 2 as we go to positive infinity. And so this is like an S shape, kind of does like this, curves up through the origin, then it goes out towards positive infinity that way. Okay, so that's the graph of arctangent, and that's why we get those specific values as our limits at infinity and negative infinity now. Any questions about those limits? All right. So now we want to find the limit as x approaches 2 from the right of the arctangent of 1 over x minus 2. All right, so here's what we have to think about in this case. As x approaches 2 from the right, what's happening to the value inside of your arctangent here? Okay, it is going to be a positive value, right? And specifically, it's going to be approaching positive what? Infinity, right? Because as I get closer and closer and closer to 2 from the right-hand side, this denominator is getting really, really small, really close to 0, and 1 over that really small value is going to blow up really fast and approach positive infinity, right? It is going to be positive since we're approaching 2 from the right-hand side. So that value in the denominator is always going to stay positive. So what we're really looking at then is the limit as some t value approaches infinity for the arctangent of t, right? So I'm basically saying that fraction I know is approaching infinity. And so if I can think about the limit as t approaches infinity for arctangent, that's going to be my limit. Well, what do we know about the arctangent as you approach infinity? It's approaching pi over 2, right? So this limit right here is just going to be pi over 2 now. Okay. Any questions about how we got that? Okay, and just think here, right? If this had been approaching 2 from the left instead, now all of a sudden we've got values like 1.99, 1.999. That denominator is going to be negative, still approaching an infinite value, but in the negative direction. So then we would be looking at our limit as we go to negative infinity, and we'd end up with negative pi over 2 instead. Okay. All right, so here's our table that just has all of our derivatives for our inverse trig functions. We already talked about inverse sine and inverse cosine. Derivative of arc tangent now is just going to be 1 over 1 plus x squared. Okay, so notice there's no square roots or anything for that one, so it's just 1 over 1 plus x squared. Arc cosecant and arc secant, very similar, right? But just the little differences, so be careful. We have a negative 1 over x square root of x squared minus 1. And then the arc secant derivative is going to give us positive 1 over x times the square root of x squared minus 1. Okay, and then our derivative for arc cotangent is just the opposite of the arc tangent. So it's just negative 1 over 1 plus x squared. So really, if you can remember arc sine, arc tangent, and arc secant, then you know the other ones are just the opposites, right? You just have to add a negative to the other three. And I'm not going to spend a ton of time there, right? This is in the slides. The slides are posted, right? So if you need to go back and look at any of these, they're also in the textbook too if you want to look there. All right. So now we want to find the derivative for 1 over the arc sine of x. All right, so first things first, let's think about how we could rewrite this function to make the derivative easier to find. So if you've got 1 over arc sine of x, what's another way we could write that? Okay, so be careful, right? It's not the same thing as sine, right? So the reciprocal of sine would actually be cosecant, right? And that's not the same thing as 1 over arc sine. Tell me this. What if we just had like 1 over x? What's another way I could write that? Yeah, this is the same thing as x to the negative 1 power. So we want to do the same thing here so that we can just use our power rule to find our derivative. So this is just going to be arc sine of x to the negative 1. So whenever you've got a value in the denominator like that, okay, just think of it as that to the negative 1 power, and then we can just use power rule to help us find our derivative. Now, this is going to be a u substitution, right? Because we are going to need the derivative of the inside. So if you want to do that, we're going to have u to the negative 1, where u is the arc sine of x. All right, so what's the derivative for arc sine of x going to give us? Good. So that's 1 over square root 1 minus x squared. And so now when we come over here and we find our derivative for y, if we do it in terms of u first, we can use power rule. So we're going to bring down the negative 1. So we get negative u. Subtract 1 from the exponent. That's going to give us a negative 2. And then we have to multiply by u prime. So now we can substitute everything back in here. So we're going to get negative arc sine of x to the negative 2 times 1 over the square root of 1 minus x squared. And at that point, right, we have the -2 in our exponent. That means we can drop it to the denominator. We already have the square root down there also. So the only thing that stays up top is the negative and the 1. So we'll have -1 over arc sine of x squared times the square root of 1 minus x squared. That is our derivative. Any questions about how we found that one? So just be careful here, right? Because it is easy to see the arc sine and think, oh, that's like sine to the -1. It's really not, though, right? Okay, that's just another indication of arc sine. And so don't think of it as an exponent itself, right? We have to find its derivative separately. And then the exponents, right? We can use our power rule on the actual exponents here. All right, now what are we going to have to use for part B? What rule? Or rules? Okay, good. It is a product rule overall, right? And within that product rule, there is going to be a chain rule because of the square root of x that we have inside the arctan. So first step, let's go ahead and figure out what f and g are going to be. So we have f is just the x. G is going to be the arctangent of the square root of x. Okay, so f prime, that one's basic. That's just 1. And so now we could do a u substitution on the g function to find its derivative. So we'll say this is the same thing as arctangent of u, where u is equal to the square root of x, or x to the 1/2. All right, so then just to remind you, derivative for arctangent is right down here. So that's going to be 1 over 1 plus u squared in this case. So we'll get 1 over 1 plus u squared times the derivative of u, which is 1/2 x to the -1/2. I'll bring this down. 1 over 1 plus u squared times u prime. And so our g prime now, if we plug everything back in, it's going to give us 1 over 1 plus x to the 1/2 squared times 1/2 x to the -1/2. And then if you want to go ahead and clean that up before you actually start substituting it in, sorry, I'm going to write it down here so it's not so squeezed in there. The x to the -1/2 we can bring to the bottom. The 2's already down there. The only thing up top is a 1. So this is going to give us 1 over 2x to the 1/2 times 1 plus x to the 1/2 squared is just going to be an x. So that's just 1 plus x now. And so all of that gave me that. And you could distribute the 2x to the 1/2 there if you really wanted to, or you could leave it alone, leave it like that factored. Okay. All right, so now it's a product rule, so now we can just plug into that. So we're going to start with our f function. which is x. We're going to multiply that by the g prime that we just found here. So that's 1 over 2x to the 1/2 times 1 plus x plus, then we go to our g function, which is arctangent of the square root of x times f prime, which is just 1. Okay, so then overall, we can just put the x in the numerator of this first one here, so that'll give us x over 2x to the 1/2 times 1 plus x plus arctangent of the square root of x. And again, if you want to change the x to the 1/2 back to a square root, you could do that. If you really want to distribute the x to the 1/2, you could do that also. Okay, but that answer right there is perfectly fine. Oh, the other thing the book did, they combined the x to the first and the x to the 1/2 in the denominator. You could do that too. That would just give you a square root of x up top, and the x to the 1/2 in the bottom would go away. So there's a few different ways you could simplify that if you wanted to. Any questions on that one, though? All right, we're going to skip 6. Okay, now we're going to start looking at some antiderivatives. Okay, so now we're looking at the integral for 1 over square root of 1 minus x squared dx. That's just going to give us arc sine, right? Because the derivative of arc sine should give us what's inside there. And again, because it's an indefinite integral, we just have to remember the plus c. And same thing with the second one here. Okay, the integral of 1 over x squared plus 1 dx is just going to give us the arctangent. Again, because it's indefinite, don't forget the plus c. Now, they don't do the if you have a negative inside there, because technically, remember, you could bring the negative outside the integral. So that first one could either, if you put a negative in there, let's say there was like the integral of negative 1 over square root of 1 minus x squared dx, you could just bring the negative out and get negative arc sine of x plus c. Or we know that the antiderivative of that one right there would also be equal to arc cosine of x plus c. So either one of those answers is correct, right? So it doesn't really matter which one you write there. And I'll be very honest, I'm not going to give you anything with arc secant and arc cosecant. Okay, so if you just know the ones for arc sine and arc tangent, you should be okay. All right, so let's see if we can evaluate this integral here from 0 to 1/4 of 1 over the square root of 1 minus 4x squared. All right, now looking at this one, is this in a form where we can just find the antiderivative? So does it match anything that we've seen so far? Exactly, right? It's not exact, but it's very close to arc sine, right? So we can probably guess that we're going to get an arc sine out of this, but we can't just say that it's the arc sine of something because we don't have just an x squared right here. We have a 4x squared in there. So what we're going to have to do is we're going to do a u substitution like we normally would, okay? And we're going to let u in this case, I'm actually going to start with u squared since I know I want to replace that 4x squared with u squared. Okay, so I'm going to say that u squared is equal to 4x squared so that then I can rewrite this integral as 1 over the square root of 1 minus u squared. Because I know that that's going to give me the arc sine of u. Now, the question is, what else do we need to replace at this point so that we can actually evaluate this integral? Okay, we can rewrite our limits, and we also need to replace what, though? The dx, right? It doesn't just become du, though, right? So we're going to have to come over here and do some work to figure out what dx is actually equal to, right? So don't just assume it's going to go straight to du. So to figure that out, I need to get u by itself first. So how would I get u? Take the square root, right? So I'm going to take the square root of both sides. It's going to give us u equals square root of 4 is 2, square root of x squared is x. So our u value this time is actually just 2x. Now I'm going to find du dx. What's our derivative going to be here? Good. So this is just going to give us 2. Now I need to replace dx, so I want to get dx by itself, so I'm going to move it to the other side. Du equals 2 dx. And now I need to get rid of that 2, so I'm going to divide. So we get 1/2 du equals dx. So now in place of dx, I can put 1/2 du. So I'll put my 1/2 out here, and then we'll have our du right here. So again, it's very similar to the u substitutions we've done in the past, except now instead of substituting for an entire inside function, we're just trying to figure out how can we make this thing look like one of our formulas. And so figure out what looks off and replace it with a u squared, okay? Any questions up to that point? All right, now like you said, we do need to change the limits of integration, so let's go through and do that. I'll start with my lower limit. So I'm going to plug in 0. Again, we're plugging it into the u equation, right? Because that's what we're trying to actually substitute here. So this is going to be 2 times 0. So my lower limit's still going to be 0. And then for our upper limit, 2 times 1/4, which is 1/2. So this becomes 1/2. All right. Now that I have my new limits of integration, what's the antiderivative going to be for what we have inside here now? So we already said the antiderivative for 1 over the square root of 1 minus u squared, that part's going to give us what? All right, so you went all the way and substituted everything, right? So I just want everything in terms of u for right now, right? So I know I'm going to keep my 1/2. This piece right here is going to give us the arc sine of u, and I'm evaluating that from 0 to 1/2. So again, just keep the 1/2 as the coefficient. That 1 over square root of 1 minus u squared, that is our arc sine formula we just saw on the last slide. So that gives us arc sine of u. And then we're evaluating from 0 to 1/2. Now we can substitute, right? So we're going to have 1/2 arc sine of 1/2 minus 1/2 the arc sine of 0. Now, these are specific values. We can actually calculate all of them. Okay, so what is this going to give us? Let's look at the first term. We have 1/2 times, what's the arc sine of 1/2? We actually did this one earlier. That was pi over 6, right? So again, we're looking for the angle whose sine is 1/2. That gives us pi over 6 minus 1/2. What's the arc sine of 0? 0, right? So the angle whose sine is 0 is 0. That's just going to give us 0 down there. So we really just end up with 1/2 times pi over 6. So that should just give us pi over 12. And that would be our answer. Okay, so that's why you need to know how to calculate these inverse trig functions, is because once we get them out of our antiderivatives, then you're going to have to substitute in, and you might need to be able to simplify those to get an exact value. Okay. Any questions on that one now? All right. Example 8. So now we want to evaluate this integral. We've got 1 over x squared plus a squared dx. So a here just represents some real number. And again, obviously this is not one of the forms that we've seen, and so we've got to think about how we're going to rewrite it in one of those forms so we can actually evaluate the integral. All right, so first things first. What does this almost look like? So if you had to take a guess at which form we're trying to get it into, which one does it seem to match most closely? Good. It's going to be arctangent, right? Because that would just be 1 over x squared plus 1 would be good to go. The problem is we don't have a 1 there. We have an a squared there. So what we're going to want to do is try to rewrite this so that there is a 1 there instead. All right. Now, it's not obvious exactly what we're going to do, because what we're really trying to do in this case is derive a formula that we're going to look at on the next slide. So I'm going to rewrite this now as 1 over, and so that I can make this right here a 1, I'm going to factor out an a squared in my denominator. Okay, so I'm going to pull out a squared, and then I'm going to think about what's actually left over from each term if I do that. Well, for sure, down here at the end, we're going to have a plus 1. Right? So if I factor out an a squared from that term, I just get 1. The question is, if I factor out a squared from x squared, what am I going to get? Exactly, right? So this is just x squared over a squared, because if I redistribute now, the a squares would cancel. That would give me x squared. A squared times 1 would give me a squared. Okay, so that's our first step. Now, I also want to think of that first term as a u value, right, that's being squared. So I'm going to write this as 1 over a squared times, and in here now I'm just going to write this as x over a all squared plus 1. Okay, so I'm basically just taking the square out, right, and just making that x over a all squared. All right, so at that point, I'm going to do a u substitution now, and I'm going to let u be that x over a so that I can rewrite this as u squared plus 1 instead. Okay, so I'm going to have 1 over, and inside here now I'm going to have u squared plus 1, where u is equal to x over a. I dropped my dx. Make sure all the way through here now, those first two steps should have a dx. All right, so now the question is, if we're trying to rewrite this in terms of u, what are we missing? What do we need to replace now? Okay, so we know we've got to get this dx in here somehow, right? But we also have this a squared down here in the denominator that we've got to do something with. So those are the two things we're trying to get. Well, what would the derivative of u be equal to this time? So remember, a is a real number. So if we have x over a, and you're finding the derivative of that, what would it be? Exactly, right? It's just going to be 1 over a, because another way to write this is just 1 over a times x, where 1 over a is just a coefficient of x now, so our derivative is going to be 1 over a. Or a to the negative 1, however you want to write that. Now, we're trying to replace dx and an a squared that's in the denominator. The problem is we don't get an a squared, we only get an a down there. So what we're going to have to do now is say, well, I need another a. It's a real number though, right? So I'm going to put another a on the outside in the denominator just to make sure I've got what I need. The other a and the dx, right, the a in the denominator and the dx are going to become du. So now I have my du. So basically I've taken one of those a's along with the dx and turned it into a du. The other a I just brought outside because it's a real number and I can bring coefficients to the front. You could even just leave it inside if you want to, right? And just say this is 1 over a times that. So wherever you want to write it's fine. Okay, but only one of those a's goes with the dx to become a du. The other a we got to keep. Any questions up to that point? Because that's the trickiest step to kind of see how we're going to get everything we need in there. Again, the reason we don't have to have everything just in terms of u is because a itself is a real number, right? It's not a variable, so we can leave it as a. All right, so now we have 1 over a, which is a real number. So when you find the antiderivative, we're going to keep that coefficient. What's the antiderivative for 1 over u squared plus 1 going to give us? That's our arctangent, right? So this is arctangent of u. Good, and because it's indefinite, we need the plus c. And then our last step, we're just going to plug the u value back in. So we end up with 1 over a times the arctangent of x over a plus c. So there's our answer. And again, the whole reason for this example is to derive a formula now that we can use no matter what a value happens to be there, right? So if it looks like it could be an arctangent, but you've got something other than 1 there, then we can actually just use this formula now, find your a value, and just plug it all into that, and we're good to go. So you don't have to do all these steps every single time. Any questions on that one? All right, so there is that formula. So if you have the antiderivative or the integral of 1 over x squared plus a squared dx, then we can just say that's 1 over a, arctangent, x over a plus c. All right, so here's our last example. We want to find the integral of x over x to the 4th plus 9 dx. All right, so we're close, right? We can almost just do this using that formula. The difference now is we don't have an x squared down here, we have an x to the 4th. So we are going to have to do a u substitution on top of just using the formula with the a value here. So again, I'm always going to say u squared equals whatever I'm trying to replace, which in this case is x to the 4th. Okay. Now, first step, we need to get u by itself. So I'm going to take my square root. What's the square root going to give us as our u value now? Good. So u is just going to be x squared, which means du dx is going to be equal to what? 2x. Perfect. All right, now let's start rewriting this thing just so we can see what we've got so far. So we know x to the 4th is going to become u squared plus, and we need to know what our a value actually is here. So we know that a squared is equal to 9, which means that a is going to be equal to what? 3, right? So the actual a value is going to be 3. We're missing an x and a dx now, so we need to replace those. So I'm going to move the dx to the other side. Gives us 2x dx. Divide by the 2. 1/2 du equals x dx. And so now we're going to have a 1/2 and a du, and we have our 1 in the numerator that we want here. Now we can use our formula, right? So if we go back and think about it, keep your 1/2. Oops. And now we're just following this formula right here because we have our u squared, we have our a squared, and so we can just plug right into this. X becomes a u, a becomes the actual a value. So we're going to get 1 over 3 times the arctangent of u over 3, and then plus c. And then finally, we can just multiply the 1/2 and the 1/3. That's going to give us 1 over 6 arctangent. And now I can plug my u value in. So that's going to be x squared over 3 and plus c. And so this would be our final answer now. So again, figure out what form it looks like. In this case, it looks like an arctangent. Think about how we can get this first piece to be a u squared, right? So we set u squared equal to that. Then because we have a number other than 1 here, we have to figure out our a value so we can use our formula. Take your derivative, figure out what you're still missing, substitute everything in there, and then you should be able to apply the formula once you get everything in terms of u's. Any questions on that one? All right. That's it. Okay, so that's all the information we're going to cover in this course. So like I said, tomorrow we will take time to go through the exam review. Hopefully I can get through all of it. If not, then again, I'll meet on Monday and we'll finish it up. But again, I do have time next week also if you do want to meet individually. So just email me and let me know if you want to set aside some time to talk about anything before you take your final exam. Don't forget, test 5 will be posted at midnight tonight. Feel free to sit down and take that whenever you want. There is no time limit, and just make sure you get it submitted by Wednesday of next week. Same thing with the homework. Just make sure that's done by Tuesday of next week. If you have questions, send me those questions. The earlier you get that stuff done, the quicker I'll be able to grade it, though, and then I can update your grades and let you know where you stand going into the final if you want to do that before the final exam. Okay, so it doesn't have to be done before the final, but if you want to know what your grade is going into the final, then I just need those 2 assignments before that. Okay, I think that's all I've got. Let me know if you got any questions. Otherwise, have a great afternoon, and I will see you all tomorrow.